I am going to present the paper with the title In the Hand of the Beholder, Comparing Interactive Proof Visualizations. And what I'm going to share with you is the result of several user studies that we did. But before diving into that, I would like to briefly introduce the topic that this paper addresses. So the question that we started with is, how can we explain automated decisions? Basically, this is just a very broad question. And the setting that we are considering this question in is simply when we have our knowledge represented in a fragment of first order logic. In particular, we're going to tackle this question in the setting of description logic. And we say that an explanation that we want to provide is simply a formal proof. Now, in previous, so last year in XLoKR, my colleague actually presented a paper that actually showed in its user study that explanations in form of small proofs are more desirable as explanation rather than longer ones. But we can do more than that. So this is an example from SNOMED ontology, a medical ontology that describes medical terminologies. And this example used to hold in previous versions. And what it stated there was that an amputation of a finger is an amputation which is located in a finger structure. And in the same spirit, it defines the amputation of a hand, and it's an amputation that is located in a hand structure. And we also know that every part of a hand is a hand structure, which is a part of the entire hand. And finally, every finger structure is part of a hand. Now, from this knowledge, the following follows, that whenever we have an amputation for a finger, then we have an amputation of a hand. Now, this is obviously dangerous, and this is something we don't want to have. And now we want to explain this. Now, it can be it's a valid explanation just to provide these 4 sentences. It's just concise, small, and this is the minimal knowledge that we have in our ontology that entails this sentence. And this is what we call a justification. Now, the problem here is that it's not straightforward to see how these sentences, how these axioms are interacting with each other to actually come to the conclusion that every amputation of a finger is an amputation of a hand. But on the other hand, the formal proof have this advantage. It can show stepwise how we can get to the final conclusion. What we see here is an example of such a proof, and it has tree structure, and the sentences are using description logic syntax. So this is one way we can represent a proof, but we can also have it as text-based, just a collection of sentences, make paragraphs, and all these paragraphs can give us the formal proof. Now, what I'm hoping to convey here is that explaining these logical inferences is not a straightforward task. And in these examples, these proofs were relatively small. So once they get larger, it becomes even more harder to understand what they are saying. And this now leads us to a more specific question, is that how can we represent these formal proofs in a more understandable way for users? And so we need to address several aspects here. So which representation of a proof should we consider? And what are we exactly allowed to say in our knowledge? So basically, what are we allowed to say in our proof? What is the level of expressivity that we're considering? And how can we manage to to actually measure the understandability of these explanations. And finally, who are the people that we are addressing? So just a brief intro into the basic syntactic level of this description logic. So what we call concept names, basically these are nouns that we use capitalized, so something like bird in the car. And we usually use verbs to refer to roles, so role names. And once we have these names, we can now express more concept expressions, something that says like the objects, that there exists something they sit in, which is a cage. And when we have these complex concepts, now we can make our sentences, our axioms. And as in the previous example, we can say that every finger structure is a part of a hand. Now, why am I talking about this? I just want to tell you how we eventually get to the proofs that we use in our study. And now, once we have these axioms, we can use whichever way we want to get the proofs. But for example, here I'm introducing some examples about consequence-based reasoning rules. And once we have the instantiation of these rules with the knowledge that we have, we can then build our proofs. And another step on top of that, now we're moving from the DL syntax to providing text-based sentences, and we can translate each of these axioms into a corresponding sentence. And at the end, we just join these sentences by connecting words, and we get our paragraphs, which then we will combine all into these text-based proofs. Okay, so now we have our proofs that we will use. But now we still need to figure out how do we measure understandability. And to assess cognitive ability, we use something called International Cognitive Ability Resource Questionnaire, ICAR for short. And this is simply a test where participants are asked a bunch of questions that look like this. So something like if you are given these shapes, what is the next in this sequence? You need to choose one of these, or you have a sequence of letters, what comes next, and so on. And based on the result or the score of this test, one can assess the cognitive ability of participants. And in this pre-study that we did, we had 101 participants. The age ranged between 18 and 48. And the main hypothesis that we had here is that this test, the ICAR 16, actually can predict the performance a user can have in the logical tasks, so understanding logical proofs. And the data that we collected actually supports this hypothesis. And by getting this result, by showing actually a relation between understanding proofs and the cognitive ability of a participant, we can address the other question. So who are our users? Basically, now we can divide users into two groups, like people with high ICAR score and with a low one. Okay, so now we can move to the main study. And the purpose here, what we are trying to achieve is that to find the difference between the preference and the performance of users with respect to different proof representations, with respect to the different type of users that we're showing these proofs. So what we're trying to establish here, that different representations are suited for different type of users. And in this study, we had 173 participants in age range between 18 and 65. And the main hypothesis that we have here is that it is easier to understand interactive proofs in comparison with static ones. And the understanding of proofs which are tree-shaped versus the proofs that are in text-based depends on the cognitive ability of the user. Okay, so what are the different representations that we are considering in this study? We have the 4 different conditions for proofs. So either we have static tree proofs or interactive ones, and static text proofs or interactive text proofs. And what we assumed or hypothesized is that people with higher ICAR score would prefer proofs in tree-shape format, basically. Okay, so each of the participants saw the 4 different types, but each representation represents a different proof. So proofs were not repeated. But before I share the results with you, I want just to talk about one thing. So there was a decision to be made at the beginning, is that what kind of topic, what's the domain that these proofs should talk about? So if we would go with something that everyone would have basic knowledge, some topics that are common, we might have the problem that people would not consider reading the proof to understand why certain thing follows, but it would simply make sense. So having a topic where everyone has knowledge about would not be ideal. Okay, so we can actually still take some terms that everyone know, but put it in a weird context. So for example, we can talk about pigs having wings and they live in the depths of the oceans and stuff like that. But there would also be a problem there that we might confuse people. So we add an extra level of difficulty on understanding the proof that it can be avoided. So what we ended up with is to go with made up names. So with this, we eliminate the use of any prior knowledge. So participants need to actually read the proofs and understand them. And at the same time, we will not make their prior knowledge conflict with the setting presented in the proof and then make things harder. So what we end up talking about is things like opties and chias and things that are horned with ferns and just made up words. Okay, so unfortunately, the hypothesis that understanding interactive proofs is much easier than static one is something we could not confirm. And the same holds for the other hypothesis. So we could not, with the data that we collected, confirm that tree-shaped proofs versus text-based proofs is something related to the cognitive ability of the receiver, of the user, basically. Now, this does not mean that these hypotheses are wrong. It's just that we need to do better in trying to evaluate this, to confirm this. Okay, so this is for the rating of the performance. We also asked the participants to rank the different representations that they saw from least to most understandable. And these are the numbers which we can draw these conclusions from. So among all participants, what we got is that interactive trees, proofs as interactive trees, were more preferable than interactive text and static text. And static trees were also ranked much higher than static text. And if we just look into the group of high ICAR score, we get that static trees and interactive trees were both ranked much higher than static text. Okay, so this is for the quantitative part. So we ask also the participants to provide us with, like, if they have additional comments about what they experienced in the study. And some of the comments were positive, in a sense that they say with using these interactive proofs, or even just tree proofs, help them understand better the proof on what was happening, how these things got derived. But at the same time, unfortunately, there was some negative experiences. And some said changing the vocabulary constantly in such a short time is giving me a headache. This kind of gives a headache. Non-existing words started to mess up with one another. And even one wrote, when will this stop? So unfortunately, our choice of abstracting into this made up words backfired and caused what we were trying to avoid in the first place, to make things more complicated than they should be. Okay, so yeah, last thing I want just to share with you is just to show you what kind of interaction in the proof we allowed the users to have, the participants. And this is an example of what the participants were seeing. So green sentences basically represent what we have in our ontology, the blue ones, what is being inferred, and this is the final conclusion for which we have the proof. And every sentence, every axiom, the users have the options to either look directly into the inference step, so just like hide everything but the immediate inference step, or just, okay, just collapse everything, I want to consider the rest of the proof, or just look into this particular subtree. So just basic functionalities, not to overwhelm the users with so many interactive things, but at the same time to give an advantage over the static ones. And the same for the text-based. So users were able to just like go through the sentences that make the proof, and every sentence by clicking on it, the premise of the inference rule that led to it would be highlighted, and then participants would be able to see where this sentence comes from in the proof. Okay, so well, yeah, I would like to conclude with just highlighting some of the things that I talked about. So cognitive ability, the way it is assessed using this test, this ICAR test. So we showed that it can predict how well would someone perform in the task related to understanding a proof. In general, trees were preferred over plain text, whether it's interactive or static. Unfortunately, showing that the relation between the proof representation and the understandability of such proof was not confirmed. And the limitations that we had in our study, one would be that the field of study for the participants and their experience with logic was something that was not considered. And as I said before, using these made up names was not like it did not serve the purpose as we had hoped for. Yeah, so from my side, that's it. And then thank you for your attention.